Hi everybody, back to solve problems, fields and webs in communication electronics by Ramo and Winery and Van Duzer again. This 1 week still working on problems at the end of chapter 1. For this part, it's going to be about the potential difference or the work done by electric fields, as well as the Gauss law, and also boundary conditions problems. Let's get started with problem number 1.7b. A point chart Q is located at the origin of a system of rectangular coordinates. Asks you to evaluate line integral E.dl. Actually, this one is going to be a relation between the potential phi that's equal to negative line integral of electric field in the xy plane, first along the x-axis from x equal to 1 to x equal to 2, and next along a rectangular path as follows. So you start from along a straight line from the point 1, 0 on the x-axis to the point 1 over 2 or 1.5 along a straight line from 1, 1.5 to 1.5 along a straight line from 2, 1.5 to 2.0. So actually they want you to compare you take the path. Doesn't matter what path you're going to take for line integration. Either starting point and the ending point is the same. You get the same result. So that's why I wrote down here it should be conservative for both line path integration. So you have you want to compare two different paths. One straight line from x equal to 1 to x equal to 2, and the other one is you take the path from 1, 0 and you are back to 0. That's going to be a longer path. Okay, here let's take a look at the diagram here. You have the point chart at the origin of 0, 0, and I wrote down the electric field at arbitrary point xy. That's going to be E equal to Ex with the unit vector Ax plus Dy. That means electric fields component on the y-axis, and that unit vector Ay. From Coulomb's law, you know that E equal to Q over 4 pi epsilon r squared, and to show the direction you also put the unit vector of r, and r is the pointing out from the origin to the particular point that you're looking for electric field. And also your r you can find from the triangle here. So your r, that's the magnitude, is going to be the square root of x squared plus y squared. And for EX, that's going to be E cosine theta, right, along the x-axis. And also for EY, that's going to be E sine theta. So you just collect some information to do the calculations. Now, you know what is your sine theta is in the term of x and y and r, as well as the cosine theta. So in the complete term of our electric field does have our x and y components. Your Ex is going to be your Q, actually I have just right here, over 4 pi epsilon multiplied by x over r to the cube. You're wondering, right, where yr to the power third. That's because you have another term cosine theta, which is equal to x over r, and you have r squared by r. That's give you r to the cube. Okay, so you have already have our electric field in for the x component and y component. So let's move on. The first condition is actually to do integration along the x-axis from x equal to 1 to x equal to 2. So that's go like straight line. So your line integration E dot dl, that's going to be your I wrote down as the complete term. This one is E and this one is dl. Since your dy equal to 0 because you move along all the x-axis, so dy ay drop out, and you have only integration of ex dx. Okay, ex and dx, and start from x 1 to x equal to 2. So you just plug in your ex and do integration. Actually, if you can take a look at this, you can represent by y by 0. So for the denominator, you end up with x to the cube, right? And x, you end up with x to negative 2 dx. You can do integration, just about math. It's taking a bit from 1 to 2. So you end up with your v actually become a negative integration of E dot dl, going to be q over 8 pi epsilon. Now we are going to do the next line integration path. So we're going to start from point 1, 0, go to the point 1, 1.5, and then go to the path number 2, go to the path number 3, and back to 2.0, sorry, to 0. So your line integration is going to be 3 paths. And for the path number 1, you have already y, right? Because x doesn't change. So you end up with dl equal to dy. and with the component ey. For the path number 2, your dy doesn't change, so you have only dx and ex. And the path number 3, your dx equal to 0, so you have only dy and ey. And I rewrite ex and ey just for doing integration. Let's take a look at path number 1. You move when your dx equal to 0, dx doesn't change, only y change from 0 to 1 over 2. So you have this term dy dy, and you pick up your ey, put in integration, and you end up with this term. To do that integration, I let v equal to 1 plus y squared. So you get v equal to y dy, or your y dy here is equal to dv over 2. And you also need to change the limit of integration. Sorry, I have to explain a lot of details for somebody who try to recall about math, especially for the integration, and have different forms. You can do faster than this. And for the limit of integration, since v equal to 1 plus y squared, when your y equal to 0, you see that your v simply equal to 1. For y equal to 1.5, this is going to be 1 plus 1 over 4. So that's give you a 5 over 4. Then for the integration, y dy over 1 plus y squared to the power 3 over 2, you end up with that's your dv over 2 is actually y dy. And for the denominator, that's become v to the power of 3 over 2. And you can do integration, so you end up with v to the power negative 3 over 2 plus 1 divided by negative 3 over 2 plus 1. And you take the lower limit and the upper limit of integration. Finally, I got the line integration of the path number 1 equal to q over 4 pi epsilon multiplied by 1 minus square root 4 over 5. Okay, so that's become the line integration of the path number 1. Now let's move to the path number 2. You do the same thing, but in this case your dy equal to 0, or y doesn't change, so you end up only your ex component and dx. You plug in your ex. You have your ex equal to q over 4 pi epsilon x over r to the cube. And I do the same thing. Let v equal to x squared plus 1 over 4, because now your y equal to what? 1 over 2, right? Because you want to do the integration along this path when y is constant, and that's equal to 1 over 2. So you put y as the 1 over 2. And that's y squared gives you 1 over 4. Now you change the limit of integration for lower limit of x. When x equal to 1, that's give you v equal to 5 over 4. And upper limit when x equal to 2, that's give you v equal to 17 over 4. Then you can do the integration, and finally I have for the line integration of the path number 2 equal to q over 2 pi epsilon multiplied by 1 over square root 5 minus 1 over square root 17. Now we're doing integration of through the path number 3. It is start from the point to 1.5 to 0. So it's back to the ending point. Again, for the path number 3, you know that your dx doesn't change, so your dx disappear. You end up with only y component of electric field and dy. And you do the same thing for let v equal to 4 plus y squared. For lower limit y equal to 1 over 2, that's give you v lower limit of integration to be 17 over 4. And for upper limit of y equal to 0, this one's give you v equal to 4. And I end up with the line integration of the path number 3 equal to q over 4 pi epsilon multiplied by 2 over square root 17 minus 1 over 2. And now if you want to compare, that we worked out this before, to do the line integration from the path from point 1, 0 to 2, 0 straight. And the second one that we worked out on the line integration, you can add them up. Integration of E dot dl is going to be equal to the line integration of the path number 1 plus the line integration of the path number 2 plus the line integration of the path number 3. So I add them up. And then finally I have my line integration of electric field equal to q over 4 pi epsilon. And that's the meet the line integration of the first one. Okay, this is q over 4 pi epsilon. So you're back to the path, the previous one, this we were before. This also gives you q over 8 pi epsilon. So that's why we say that conserve. So this problem we actually work out on the line integration or integration of E dot dl, which is related directly to the potential difference. We will see example in the next problems. Next, problem 1.8b. A shard of a surface density log s is spread uniformly over a spherical surface of radius a. Find the potential for r less than a and for r greater than a by integrating contributions from the differential elements of charge. check the results by making use of Gauss' law and the symmetry of the problem. Okay. Now we're going to work on potential. Let's get back to the definition of the potential. Be represented by phi. The potential actually is the work done by electric field. Okay, you move 1 point charge or 1 Coulomb charge from point 1 to point 2. You can find the potential difference between the point 1 and point 2, or the work done, that you need to apply work to move the 1 Coulomb charge. Or you can write, actually I'm missing a negative sign here, sorry. So your potential difference is going to be the line integration of E dot dl. And from Coulomb's law, the phi, actually this is the simple equation that you can use for a system that's not so complicated. That's going to be dq by 4 pi epsilon r. Now we start working on the problem. dq actually become the charge density multiplied by the small area, which is the ds. Now for spherical coordinate, you can see the picture. This is the sphere. There's no charge inside the sphere. It's not a solid sphere. The sphere is accumulate only on the surface of the sphere. For the spherical coordinate, your ds, that's going to be a square sine theta d phi. You need to go back to take a look how to calculate for the volume of in the spherical coordinate and the surface of the spherical coordinate, where your phi actually is the anchor you turn around on. For this part, you can imagine it's going to be on the xy plane. Sorry, on the x plane. And that become a square sine theta d theta d phi, where a is going to be the center point of the spherical to the surface element, and that's actually become a, or the radius of the sphere, so don't get confused. And for r, from the triangle here and applying Cauchy's law, you know that, sorry, I'm missing r here, your r, the magnitude of the vector r minus vector a, just give you the length or the observing point to the charge element, or the distance that you are looking for. In this case is r, from Coulomb's law. The Cauchy law stated that if this one is theta, the magnitude of the vector r minus vector a going to be r squared, the opposite side of triangle, plus a squared, and then minus 2r multiplied by a multiplied by cosine theta. That's the Cauchy law. Now you should be able to calculate for the potential different. Okay, so since the UDV equal to this term, and the magnitude of vector r minus vector a equal to this term, so your phi, you simply do integration, with respect to the phi and the theta. To make integration easier, I let this term to be v, and your v become negative 2ra psi theta, this theta, or your psi theta that you have right here, going to be dv over negative 2ra. You have to be careful about the calculation because there are so many steps that you have to work through. So be patient, otherwise you will get the wrong answer. Okay, you can follow the way I do integration. And this one is going to be v negative 1 over 2. So when you do integration, you plus 1 divided by minus 1 over 2 plus 1. And take limit of integration from v1 to v2. Now take a look at v1 and v2. Since for theta you do integration from limit of integration is from 0 to pi. When theta is pi, you take a look at the equation. This means your cosine theta equal to negative 1. This give you plus 1 or 2ra. For theta equal to 0, this term become 1, so you have a negative side here. Or r squared plus a squared plus 2ra, that give you r plus a squared. And this one, for theta equals 0, you end up with r minus a squared. Then your phi, from your integration, you just take the limit of integration. You end up with phi equal to rho is a multiplied by 2a over 2 epsilon r. Finally, you have phi equal to rho is a squared over epsilon r. Okay, so this is your potential distribution that you are looking for. Now they have something to consider. We're not really finished yet because you have two different regions that you are looking for the potential different. See, for r less than a, that means inside the sphere, and for r is greater than a, that means outside the sphere. So consider the situation here. From Gauss' law, you know that the closed surface integration d dot ds, d is the flux, electric flux density, ds is the area, the small area, or d equal to epsilon e equal to q enclosed, or the total charge in the unit of Coulomb inside the closed surface. And you also have the relation between electric field and the potential difference. That is the E equal to negative d phi over dr. If this one is only in one dimension, or in the complete term, you have what's that? Sorry. I forgot. Sorry. You have this term actually is come from what? Divergent. Sorry. del V, right? If I'm not wrong, that's the equal to negative E. So that's why you have E equal to negative dV over dr. Let's consider outside the sphere, because the Q enclosed not equal to 0, phi is not a constant. You take a look at the equation. If Q enclosed equal to 0, that means your E going to be 0. So that means your E is not equal to 0. And your phi is not constant. So you can use this term to represent phi at any r. And if you take a look at if take limit r go to infinity, your phi equal to 0. So that's agreed, right? When you're far away from the charge, your potential that's going to be 0. Now for the inside the sphere, you know exactly that your Q enclosed equal to 0. So that results in E equal to 0. And from this equation, for E equal to 0, that means your potential is going to be a constant. So you can plug in R equal to A. You end up with the phi at any point R inside the sphere going to be as A over epsilon. So your potential going to be the same everywhere inside the sphere. Now similarly, they ask you to plot I'm not sure if I'm missing something or not. Okay, that's you already finished. Seems like I'm missing one page of the problem. This one is for the problem 1.8. So we already finished. Okay, so we will continue our problem 1.8f. That's going to be about the potential as well, but we will also talking about the boundary condition of electric flux density. Okay, I'll see you in the next YouTube series. Bye.